Now next we will see under electrovalency we have got variable electrovalency. Got it? Variable electrovalency means, for example, you know that there are many metals are there. For example, copper, we have got Cu plus, Cu2 plus, Fe, Fe2 plus, Fe3 plus, Sn2 plus, Sn4 plus. Similarly, Pb2 plus, Pb4 plus. Similarly, Pt2 plus, Pt4 plus. In this way, many metals are there which have got variable valencies. Alright, here we will say variable electrovalencies. Why do we say? Because it loses its electrons to form ions, that is cations. Hence, we are talking about electrovalency. Because definitely, when it is forming an ion, definitely it is going to react with a negatively charged ion to form what compound? Ionic compound. It will never form a covalent compound. So, hence we are talking about variable electrovalency, so to say. Understood? Otherwise, you may say it is variable valence. You may say, sir, I have read in lower classes variable valency. Yes, that is correct. This is variable valencies. They have got different valencies. But this particular valencies will result in the formation of what bond? Ionic bond. Because this is cation, definitely it will react with anions to form an ionic compound or ionic bond. So, hence I say it is variable electrovalency. Now, the question is not variable electrovalency. The question is why the element shows variable electrovalency. Because valency means what? It is a combining capacity of an element. So, it should be just one only valency. Why an element has got variable valency? Why iron has got valencies 2 plus and 3 plus? Why copper has got valencies Cu plus and Cu2 plus? Why tin has got Sn2 plus and Sn4 plus? That we need to understand. That we need to understand now. That why it shows variable valencies. Alright, that you need to understand. That is what I am going to discuss with you now. Alright, understood what is variable valencies? Clear? That is called as variable electrovalency. Now the factor is, now the question is that why it shows. Alright, the first point is unstable configuration of the core. The first point is unstable configuration of the core. We can say that. Unstable configuration of the core. Core means the remaining, that is the atom along with the nucleus. It is unstable. Alright, the remaining, what you can say, atom after losing electrons, the remaining atom, the atom which is being left along with the nucleus, that is called as the core. Otherwise, core means the inner part basically, but here we means to say that. Alright, that after the loss of electrons, whatever the atom is left, rather it's not an atom, of course, it is an ion. Alright, so whatever the ion is left with the nucleus, that is called as the core, and that core is unstable, and due to the unstable configuration only, it further loses electron to form a stable configuration. Now how? What does it mean? See, let us take the example of iron, Fe26. It is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Is right? 6 plus 4, 10 to 12, 6, 18 to 20, 26. This is the electronic configuration of iron, you know that. Fine. Now, what we find is that iron is having 2 electrons in the outermost shell. Can you see it? This is your outermost shell. I said you already. The highest principal quantum number determines the outermost shell. It is not necessary always that the one which is at the last, it is your outermost shell. It is not necessary. It may or it may not be. In this case, you can see it is not at the last. You may write it down. In certain books, you can see it is written 3p6, 36, and 4s2. For your convenience, you are writing. But this, when you will be writing it, it is not according to the Aufbau's principle, isn't it? So hence you write it in this way. And this much you remember. This much you remember. The highest principal quantum number will decide the outermost shell. That's it. Finished. Fine. So it is having 2 electrons in the outermost shell. It will lose 2 electrons definitely. So it is going to form what? 1s2, 2s2, 2p6, 3s2, 3p6 and 3d6. Now tell me, is it stable? You will say why it is not stable. Okay, fine. Let us see the outermost subshell. This is the outermost subshell 3D. So D has got 5 orbitals. 1, 2, 3, 4, 5 and one more here 6. I have arranged 3d6 here. You can see it here. 6, it is being arranged in this particular manner. So you know that an particular element or ion or any species, if its outermost shell is half filled, if its outermost subshell is half filled or fully filled, it is said to be stable configuration. If its outermost subshell it's half filled or fully filled, then it is said to be stable configuration. We have studied already. In case of D subshell, what it will be? Either D5 or D10. it is said to be stable. D5 or D10, it is said to be stable. I have explained you in atomic structure why it is stable. Similarly for F, it is nothing but F7 and F14. Similarly for P subshell, it will be P3 or P6. Alright, P3 means exactly half filled, D5 means exactly half filled, F7 means exactly half filled. So if it is exactly half filled or fully filled, then it is said to be stable in nature. You know that. So here it is not exactly half filled. You can see D6 is there. So definitely it will have a tendency to lose one more electron. So this is called unstable configuration of the core. See, after the loss of 2 electrons, this core which is being formed, Fe2 plus ion which is being formed, is still not stable. Why it is not stable? Because outermost subshell is partially filled. It is not what you can say partially stable, not partially filled, I am saying partially stable. So hence it is not fully stable. How it become fully stable? By losing an electron from here. So hence when it loses one more electron, Fe3 plus is being formed. 1s2, 2s2, 2p6, 3s2, 3p6 and 3d5. Alright now? Now you draw it and see the D subshell, the 3d5. See here, you draw it and see. 1, 2, 3, 4, 5. See, it's exactly half filled. I said, you know, if any particular species, if it has got D subshell as the outermost subshell, then if the configuration is D5 or D10, D5 means exactly half filled, D10 means exactly fully filled, then it is said to be stable in nature. Now you see this D5, it is stable. So understood now why it loses an electron further? Because first it loses 2 electrons in general, because outermost shell, so it will lose 2 electrons. Whatever the electrons is there in the outermost shell, it will lose. So it is losing 2 electrons. After losing the 2 electrons also, the core is not stable. This is the core, the remaining. It is not stable. You can see it here. Why it is not stable? So hence it loses further 1 electron and now you can see it becomes stable. Alright. So this is one of the reason that why an element shows variable electrovalency. This is one of the reasons. Understood? I hope so. Now next is, another point is there, inert pair effect. Inert pair effect, we can say that. What I said, the second factor due to which it shows variable electrovalency is inert pair effect, we can say that. So, it should be inert pair effect, correct. What do you mean by inert pair effect? See, if we write the electronic configuration of tin, atomic number 50, alright. So 50 means it will be helium. See here, helium, neon, argon, krypton. So helium is atomic number 2. 2 plus 8, 10 is neon. 10 plus 8, 18 is argon. 18 plus what you can say 18, because what is the number? 2, 8, 8, 18. I have told you, no? So in this way, 2, 8, 8, then 18. So first is 2, then 8 I'll add it, I'll get, that is nothing but neon, that is 10. Then another 8 I'll add it, I'll get argon, that is 18. Another 18 I'll add it, I'll get krypton, it is 36. So hence krypton, it is 36 atomic number I got it. See, it's very easy, I have told you earlier also. Now, how do you know in which subshell krypton ends? You know that all inert gases ends in P subshell, or it ends in P subshell. So helium first shell, neon second shell, argon third shell, krypton fourth shell. So it will end in 4p6. Alright, it is going to end in 4 because fourth shell you got it, and it what you can say, the outermost subshell will be P subshell because you know it belongs to P block, and outermost subshell will be fully filled because inert gas means it has to be fully filled. Understood or not? All these things we discussed with you. So krypton's configuration is Kr36, we can say that, and its outermost subshell is 4p6. Got it? How it is 4p6? See here, helium, neon, argon, krypton. 1, 2, 3, 4. So fourth shell. P subshell, because it belongs to P block and outermost subshell is fully filled. So P subshell has got maximum how many electrons? 6 electrons. It is 4p6 in that way. Fine. So after 4p, what it comes? 5s. So why I am saying all these things? Because I need to write the configuration of tin. So krypton 36, 5s2. You can write 1s2, 2s2, 2p6, 3s2. It will become very, very long. So you write it according to the nearest inert gas. I have taught you already. So krypton 36, now 5s2. 4p6, after 4p, what is that? 5s. So 36 plus 2, 38. Now after that, what you will be having? It will be 4d10 and 38 plus 10, 48. I want 50, so it is 5p2. Got it? So you got it? 5p2 in this way. Clear now? Now you listen. So tin has got 2 electrons in the outermost subshell. Now these 2 electrons it will readily lose, and it is going to form Kr36, 5s2, 4d10. 5p is gone, it loses readily. Okay, fine. Now after losing these 2 electrons, this is the outermost shell now. Definitely from 4 it is not going to lose. After losing 5, then it will reach 4. So it is going to lose from here. From here 2 electrons it is going to lose. Then only it is going to form Sn4 plus. Now listen carefully, children. Sn2 plus ions readily exist, but Sn4 plus does not exist readily in the nature. So stannic compound are very rare. Stannous compound are occasionally we are getting it. We are getting the stannous compound, what you can say, in the nature readily. But stannic, it is occasionally we are getting this particular compound like stannic oxide or stannic chloride. We are getting occasionally. The reason is after losing these 2 electrons, this electrons which is placed closer to the nucleus, because S subshell you know it is closer compared to that of the P subshell. It is closer to the nucleus. It comes under what you can say a strong internuclear force of attraction. Means it has got large effective nuclear charge upon these 2 electrons. So a huge amount of energy will be required to remove these 2 electrons. So these 2 electrons act as an inert, just like an inert gas it acts like. Because inert gas from the outermost shell, it's very difficult for you to remove electron from the outermost shell of the inert gas. Why it is going to lose? It's already stable. See, also same thing. S subshell fully filled, stable. First of all, then it is closer to the nucleus. Secondly, if it has got large amount of nuclear, what you can say, effective nuclear charge, means internuclear distance is so small and the nuclear charge is so high that for that particular purpose it holds these 2 electrons very strongly and is very difficult to remove. Hence these 2 electrons acts like an inert gas, which is otherwise known as inert pair effect, we can say that. So for that particular purpose it is going to form Sn4 plus, no doubt about it. But what I said, it is not easy. It is not easy to lose the 2 electrons. Alright, it's not easy. Understood why it is not easy? Because after the loss of 2 electrons, the nuclear charge increases. So effective nuclear charge is very high. This subshell, S subshell, fully filled, highly stable. It is not going to lose readily. Next is that it is very closer to the nucleus. These 2 electrons is held very strongly, tightly by the nucleus. As it is very closer, so hence more tightly is being held. So to remove these 2 electrons, if you remove, then only it is going to form Sn4 plus. To remove these 2 electrons, large amount of energy is required. So hence these 2 electrons behaves like an inert pair, just like inert gas. As I said it is very difficult to remove electron from the inert gas. What is? Because it is stable, highly stable. So hence for that particular purpose, Sn2 plus ions readily exist, Sn4 plus does not. Hence Sn4 plus compounds are very rare. So hence this is called as inert pair effect. So electrovalency is due to 2 reasons. One is due to unstable configuration of the core. Another is known as inert pair effect. Now next is, this is all about the electrovalent bond. I need to say something, and I said next is about the covalent bond. You've studied already the factors and all those things I've discussed with you. Now in the covalent bond, just like electrovalency, you've also got covalency. Alright, write it down. What is covalency? Covalency means what is the number of electron pairs it shares between the combining atoms is known as covalency. The number of electron pairs it shares between the combining atoms. How many electron pair it is sharing? Suppose if it is sharing 1 electron pair, covalency is 1. If it is sharing 2 electron pair, covalency is 2. Like in oxygen, 2 electron pair it shares, it is 2. In hydrogen, 1 electron pair it shares, it is 1. In nitrogen, 3 electron pair it shares, it is 3 in this way. So number of electron pair which it shares with the combining atoms is known as this covalency. So just like variable electrovalency, we have also got variable covalency. Alright, we have also got variable covalency. So what is that variable covalency? Alright, now you must be knowing that what I can say, if I ask you the valency of chlorine, you will say it is 1. But I will say you how much you know. It is 1, 3, 5 and 7. Alright, it is 1, 3, 5 and 7. The what you can say, chlorine has got variable covalency. Similarly, if I ask you for sulfur, you will say sir it is 2 because 6 is there in the outermost shell, 2 more electrons it is going to gain, right? But sulfur has got a variable covalency of 2, 4 and 6. Got it? How? How it is possible? That it is going to form 2, 4, 6, chlorine is going to form 1, 3, 5 and 7. How it is possible? Got it? That we will see in the next video. Thank you.